What's great is that Facebook has launched a brand new project, but it's proven that as these data centers, these servers are already in use. Well, I think it's much greener. The power the cloud uses is much less than the servers they've been used to the last decade. I mean, it means that the more we use the internet, the more we use the cloud, that is, I think everyone needs to be reassured that the cloud companies are working hard to become more and more energy efficient. So we have a common interest there. For most of us, we use cloud-based sites, whether it's uploading photos to Picasa or using Gmail, Facebook, or using Zynga. All these companies are enabled by cloud technologies. Every consumer wants that process to be as green as possible. And this is a big step forward today in having computing be more and more green. Data centers were considered one place where we're trying to innovate. Servers are another, software is another. We're seeing that all those three things are coming together. The idea of open source, crowdsourcing, Wikipedia, these are all part of a new era of thinking enabled by the same force, which is that when things are open, there's more innovation around them.
I'm Tom Furlong. I'm the Director of Site Operations for Facebook.
Do you work here in the data center or you work down in Palo Alto?
I'm a Palo Alto employee. My design and construction team led by Jay and my operations team led by Delphina there are the ones who built and operate. So Ken is our permanent Facebook manager here on site. You can see the light stimming. We have an LED lighting system in the building that are on sensors, so as we move around the lights will come up and they'll go down. LED is typically much more efficient than regular incandescent lighting. There are a bunch of energy efficiency features that we put in the building that aren't really a part of the Open Compute project. They're a part of our desire to be a LEED Gold certified. So LEED, Leadership in Energy Efficiency and Design is the acronym. It's a national standard. They have silver, gold, and platinum. There are all sorts of points. You basically evaluate yourself against those points. Things like we have rainwater reuse for flushing toilets. We have the LED lighting. We reuse some of the heat from the data center in the winter to warm the office itself. The main data center measures, like I showed you in the lobby, the PUE measure and the WE measure. There are lots of measures that the Green Grid and some other groups out there put out that are the real measures of efficiency for a data center. So one of the important things in an evaporative cooling system, you want to have very pure water. You charge a nozzle and you spray water out of that nozzle, and so you don't want that water to have any minerals in it or other types of biological materials or anything. So you take the water and you run it through a reverse osmosis system that gives you very, very pure water, and then that's pumped upstairs to where the cooling systems are, and there are a set of pumps up there and nozzles that then spray the water into the air to cool it down. There's a UV system that the ultraviolet light kills any biological material in the water. So that's essentially the process to get that really pure water. Essentially, the air is coming in on that end of the building. It's coming this way, and then it goes down. So each one of these rooms is a stage in the process. So I'll start down at this end, which is the true, it's coming in the building. So the main feature of this building, obviously from a cooling standpoint, is outside air. Outside air is on the other side of this grill. Essentially, this is where it comes in. You can see some movable dampers behind you. So all it does is this basically air rolls in, it goes through those dampers, and there's a succession of stages that we go through where we mix and then filter and then basically cool and then send it down in the data center. In really cold days, you don't want really cold air. So you actually take some of the air that's already gone through the servers that's warm and you reuse it. And so this is actually, below us is a plenum that has that warm air in it, and it comes up into here, and it actually gets delivered on the other side of the wall there. We'll see it on the other side, but that's where it's then mixed together. So the system is always looking at what are the conditions coming in, and then it's trying to decide what is it that I want to present to the servers. Do I need to add moisture to it? How much of the warm air do I add back into it? If it's a really hot day, you don't recirc anything. Generally, you just send it out because it's generally hotter than the air actually coming in. And then all you're doing is cooling. So you don't want the data center to be too cold, because too cold, it's not nice for the technicians, but it's also technically, the air tends to get dry and you get static electricity, which is not good for the equipment. Makes it difficult to work on. If it's too hot, we find the servers are much more resilient than we used to think they were, but quite frankly, you know, we have a temperature setting of 80.6 degrees Fahrenheit, which is our maximum temperature that we'll show in this building. We actually are now going to 85 degrees as the standard, but when we designed this, 80.6 was within a range that the American Society of Heating and Refrigeration had said was a good standard. So we went ahead and used that as our starting point. We'll probably turn up the heat in here as well, you know, let it go higher later on. But while it's new and we're testing it to the numbers that we originally created, which is 80.6 degrees. So what you're seeing right here is you're seeing basically these dampers are the recirculation. So you can kind of look here at an angle and you can feel the heat coming up. This is the, there's a 14-foot air plenum above the servers, but below this deck, which is where all the hot air goes. If we're reusing the hot air, these dampers crack open some amount and the air comes into this chamber, whereas of course it's mixed with what's coming from the next room, which is the cold stuff. And then it's going through a bank of filters. There's actually two sets of filters on here. There's a coarse filter, which is on the outside here, a relatively inexpensive filter. Underneath it is a much more expensive filter you can see from the other side. So there's a much more fine filter. Filters, filter replacement, and other things. There's a lot of air that moves through here. One of the things that we need to learn as we continue to go is how often do you replace the filters, because you have a dilemma, which is the filters tend to restrict airflow. That means your fans work harder, which means you use more energy. So you want to balance between filtering out what you need to filter out and not necessarily letting them get too dirty. So our cold air, warm air mix coming through the filters have made it through the filters. There's a set of temperature sensors here that basically are telling our system what the temperature is in this room. Based on those conditions, it's deciding how much cooling or humidification we need to add. At a higher temperature, we'd be cooling the air down. At a lower temperature, we're typically adding humidification. Same process. This MEFOG system essentially is a high-pressure pump. There's a set of nozzles up here. The nozzles come on depending on the amount of moisture you want to put in the air. I chose this section because a few of them are running here. All or some or none will be running depending on the whatever the conditions are that warrant it. That white wall right there is what we call a mist eliminator. So what it's doing is it's taking water droplets that might not have fully been incorporated into the air. It's taking water droplets and it's gathering them so that we're not sending droplets of water down into the data center. So pretty important. We'd rather not have it rain inside the data center. There's all sorts of pans and collection mechanisms along here so that we can collect and recycle the water as we need to for what hasn't been incorporated in cooling the air. So the mist eliminator on my right side here, you can feel there's no moisture carryover, just cool, somewhat moist air. The fans here are drawing that air through the system and pushing it into the next space, which then directs it down into the space below. These, what we call fan walls, have very, very highly efficient fans in them. They have small, like 5 horsepower motors. The fans will speed up or slow down depending on the amount of air that needs to get down into the space. Little fans in servers aren't terribly efficient. Big fans like these are tremendously efficient. So the way we engineer the open compute hardware is we have it such that By pressurizing the space down below, we basically suppress the fan speed in the servers themselves. So we save energy in the server by making those fans work less hard, and we work the more efficient fans harder. Where you see these railings is the open down, and you'll see it down below when we get down. That's an air shaft down into the data center itself. So in one of the features of the data center is there's no ductwork in the data center. Essentially, you go down that air shaft and you get down into the data center space, and then the air finds its path to where the servers are. This is essentially the open compute servers. What you see is what we call a triplet rack, has 90 servers in it, and another triplet rack on the other side. These two racks are served by this UPS system. We worked with a manufacturer. This is part of the Open Compute project specification that you can download from the website. You can purchase these. I believe it was Delta that worked with us on this one. The servers themselves, we have a custom power supply. It has both an AC and a DC connection to it, so that the server, and that's not terribly typical, the server can connect both to this UPS or it connects to the AC distribution system. The biggest feature in the Open Compute is the fact that we got rid of a centralized UPS system. So in a typical data center, you're taking a utility voltage, you're transforming it, you're bringing it into the data center, and you're distributing it to your servers. There are some intermediary steps there with a UPS system, with energy transformations that occur. It costs you money and energy, between about 11 and 17%. In our case, you do the same thing from the utility, but you distribute it straight to the rack. You do not have that energy transformation at a UPS or at the PDU level. You get very efficient energy to the actual server. The server itself then is taking that energy and it's making useful work out of it. It generates heat. The heat is removed from our air conditioning system, and in our case, there's no mechanical cooling to it. It's all the evaporative cooling system that we outlined in our Open Compute initiative and what I just showed you upstairs. So in this particular case, the air has come down this shaft. So I showed you above us the area with the railings around it. The air comes down the shaft. It floods the cold aisles in the data center, and you can feel it's about 72 degrees right now. It goes through the servers into the hot aisle, and what you can see behind you over here, there's plexiglass. The air goes back up into the shaft. Some of it is reused in that mixing room that we saw. Some of it is put out, just discarded to the atmosphere. The Open Compute servers, we engineered them to be very energy efficient, both in the types of voltage regulators that are used, eliminating equipment on the motherboards themselves that wasn't necessary, and architecting where we put the memory and the CPU and other things so that we could end up with the most energy, that's the easiest to cool as possible. You want a nice even airflow through the machine. The other thing is we did a lot of servers are what are called 1U height. These are 1.5. It allowed us, for the fans that we put in there, to make them more efficient. Larger fans are more efficient. The other thing is it allows us to have a taller heat sink so we can remove more heat from the processor. So everything we built, we really looked at trying to make it the most energy efficient possible. The other benefit of all of this, which I like for my technicians, is it's pretty easy to service. We put everything front accessible. There's nothing in the back that the technician needs to worry about. All you need to do to move a server tray is disconnect the power cords, disconnect the network connection. You can slide that tray right out. You can put a new tray in, or you can do something, you can do some work on it. So every time you log in as a user, these machines will render the page for you. It will look at your friends, look at what the posts are, decide what it needs to present to you, and it will help build the page. It will pull the data from caching servers that are a temporary place to locate some of that data, and from our database servers, which is where the core of the data resides in a more permanent nature. So these are what you, the user, end up interacting with. The other machines in this room typically are behind this layer, right? They interact with this layer, you interact with this layer. You never interact directly with those machines behind the scenes.